Welcome back to another problem. Let's get right into it. So what's unique about this problem is now we will be solving for the kinematics when our reference axes are themselves rotating, where previously we were only using non-rotating reference frames. So let's read the problem statement. The slotted piece rotates with an angular velocity of about 12 radians per second and an angular acceleration of 4 radians per second squared about point Q, which is right here. At the same time, point P is imparted with a constant speed of 3 meters per second, and that's given by U, and that's relative to the slotted piece. Note that point P is constrained to follow the curved slot's path, and then we are asked to determine the acceleration of point P. And then we're given some geometrical data for the length L and then also little r as measured from big R. Okay, so like I said previously, we now are working with a rotating reference frame, where previously we were using non-rotating reference frames. So just as an idea, if I had a non-rotating reference frame and I was dealing with relative velocity, because we can imagine if that green slotted mechanism is going to be moving with an angular velocity and angular acceleration, and then we're imparting point P with a constant velocity to the right, we have some relative motion going on here. So in non-rotating reference frame, for relative velocity of some random points A and B, we'd have that the points A, or the relative velocity of A and B is equal to velocity of A minus velocity of B. Whereas if I had a rotation, or a rotating reference frame, I would measure that the velocity of A with respect to B is going to be equal to the omega that the reference frame is rotating at, crossed with the relative position vector, and then plus this velocity relative term. Okay, so you can see where the differences arise. And then if you just wanted to, you could just write that the velocity of A is going to be the velocity of B plus this term here. So the point of me showing you this is just to keep in mind that we have these differences between a rotating reference frame and a non-rotating reference frame. And these differences are going to affect our solution approach or our problem approach. So as you have probably found from your textbooks, we are going to have this big equation that we're going to be working with in these types of problems. And I will box it up right here. We'll call this the 5-part acceleration equation. So what this tells us is, so if we wish to measure the acceleration of point P in this rotating reference frame, we have 5 different components to consider. So let's consider each one and then we'll solve. So point Q, that's the absolute acceleration of Q defined within the rotating reference frame itself. Alpha cross R SQ, that's the tangential acceleration of some coincident point S, as you can see I drew in the picture, in circular motion with respect to point Q. We have omega across R, and that's the normal acceleration of the coincident point S, which is in circular motion with respect to point Q. Then we have 2 omega across V relative, and that is the Coriolis acceleration. And that essentially is the difference between the acceleration of point P relative to the coincident point S as measured from non-rotating and rotating reference frames. And finally, we have our A relative term, which is the relative acceleration of P with respect to our rotating axes themselves. Okay, I hope that just helped to keep you a little bit grounded in what we're looking to solve for here. And so once you just have those different quantities kept in the back of your mind, these problems just become, or maybe not this problem classes in general, but this problem is simply plug and chug once you have those values in mind. So we'll just work at them one by one, and I'll just label them 1, 2, 3, 4, and 5. Okay? So let's just start with 1. So what is the absolute acceleration of q? Okay, I hope you said that it's 0, because that entire slotted mechanism is rotating about q. It actually has no translational acceleration at all. So we'll have that AQ is 0. Now for 2, we want to compute alpha cross r, where r is going to be that radial relative position vector of coincident point S with respect to point Q. So just zoom in a little bit more there so we can see what we're working with. So essentially, it's just going to be L, right? And we're given that's 0.75 meters, and so we want point S with respect to point Q. So that's going to be negative I hat. So R is just going to be negative 0.75 j hat. Okay? So now we'll just do alpha cross R, assuming that alpha is in the positive k hat direction. So that's just going to be 4, oh, don't need that, k hat cross negative 0.75 j hat. And if we remember our trick for doing the cross products, we just follow this little flow chart. So k cross j would give us negative I hat, but we have a negative already from the negative 0.75. So that's just going to come out to be 3 I hat. And I'll circle these two just so we have them for later reference. 3, so now we're going back to the normal acceleration of the coincident point. We have, oh wait, that's a terrible circle. Okay, there we go. We have omega cross r, which that's going to be 12 k hat cross negative 0.75 j hat. Be careful with your cross products here. So we'll have 12 k hat cross 3 I hat, or I take that back, 9 I hat, for the same reason as we had above. And then k cross I, that's going to be positive j, and we have positive scalars in the front. So that's going to be 108 j hat. Okay? Moving along. So for 4, now we're on the Coriolis acceleration. We have 2 omega cross v rel. And so that's just going to be 2 times 12 k hat cross. Okay, so what's this v relative term? We can see here that we imparted point P with a constant speed of 3 meters per second squared. So that u term, that's going to be our relative acceleration of point P with respect to our rotating reference frame. So that's simply just going to be 3. 3 in the I hat direction. So that just comes out to be 24 k hat crossed with 3 I hat, which just comes out to being 72 j hat. And finally, for 5, we want the relative acceleration. So let's see what color I made P, okay? So if I have point P here, and I want the relative acceleration, so I gave it a constant u in the positive I hat direction. And so if that's constant, we know that that is the tangential velocity. And so if we use our normal and tangential components, we would see that the tangential acceleration of point P would be 0 because it's moving with constant velocity. However, we know it has a normal component to this acceleration, which is just going to be given by Vt squared over rho, where rho is the radius of curvature. So the tangential velocity in this case is just going to be u, and then rho, the radius of curvature, so we have constant radius in this problem, that's just going to be r, which is 0.25 meters. So we'll just plug in our values here. And that comes out to being 36. But 36 what? So we know that in this problem, since P is traveling to the right, we're going to have this normal component of the acceleration pulling it down. So that's actually going to be a negative j hat direction. Okay, so now we have calculated all of our values for the 5-part acceleration equation, and now we're just going to plug in. So we're going to have AP is going to be equal to 0 plus 3 I hat, which comes from the tangential acceleration. We're going to have a plus 108 j hat, and that comes from the normal acceleration. We're going to have a plus 72 j hat from the Coriolis acceleration, and a minus 36 j hat, which comes from that relative acceleration. And so if we just combine all of our terms, we'll have, it's going to be 3 I hat plus 144 j hat, and it's going to be meters per second squared. Okay, not too bad. Again, just summarize. We have our 5-part acceleration equation because we are working with a rotating reference frame, and we have a relative motion of some body within our problem relative to said rotating reference frame. And so just by proceeding cautiously and being careful with our cross products, we solved for all 5 parts of the 5-part acceleration equation and then just solved. So yeah, that's it for this problem. I hope this was helpful, and I hope to see you around for the next video. Thank you.